So, first and foremost, I haven't posted, so let's just go over what's going to happen in the next couple of weeks. So this week is week 9. You have a timed lab this week. Week 10, we'll be going over hash tables and sets of maps. I'll be posting basically the vast majority of the videos today, except for the videos on analysis. Why is it that hash tables are constant time to add and remove? So why are those? Why do those work? And then on week 11, we will have our exam. So that should be the week of the 8th and 9th. That means that that exam will encompass. It will have a hash table question on it. Specifically, it'll have one coding question, and its form should be pretty darn familiar to everybody. So by that point, yes.
Week 11, that's the 8th or the 1st?
We are week 9, week 10, week 11. So yeah. So that is the week of the 8th. So your exam will be on the 8th. And that will be worth 15% of your grade. It is about a 60-40 split, around thereabouts, on theory questions and programming questions. Last time around, it was the other way around, where it was way more coding questions than theory questions. Okay, so this one has a lot more theory because there's a lot more terms. Your final again will probably be closer to this split, if not 50-50. Okay, now. All right, what is the others? So what else do we have to look at? So this is from last semester's practice exam. It might be the same as this semester's practice exam, but the reason I have pulled it up is because of the timed lab this week, right? So for the timed lab, we will go over some questions that are about, so I hopefully have already talked about how the timed lab will go over heaps, right? Did I mention that already? The time lab will go over heaps. About 30 of the points should be pretty simple, getting formulas from the slides and then following the slides. This is fairly straightforward if you follow the slides and watch the videos. The coding questions will deal with traversing a tree, right? Basically problem solving with a tree, and I realized that aside from two-string, you haven't had too much experience. So here I am giving you 2 questions that you can work on and get some practice on. These will be very similar to the 2 questions that I'll be asking on the timed lab. So this first question, this actually has been given on an exam. Variants have been given on the final of this, of this exact question, which is here I'm giving you a tree of integers. I want you to return the sum of all the integers stored into the tree. Okay, so it takes in. So root again over here is not the root of the entire tree. It is the root of the tree or the root of a subtree within that tree, right? So you got to figure out your base case, and then you do your recursive case, right? It's actually, so this is actually fairly straightforward. I can write this in about 4 lines of code, including the curly braces for the method body, right? It's actually fairly straightforward, this one. So the other question, another practice question in the same vein, is equals, which takes in 2 trees. So write a method which, given 2 trees or subtrees, it returns whether or not the contents of the entire tree are identical. So do tree A and tree B, not only do they store the same items, right, but is their structure and their shape exactly the same, right? Do they all go left at the same places where they'd go left and go right at the same places they'd go right? So it's a very good, so these are very good practice ones. This one's a bit tougher than I would ask on the timed lab. So, but those are the kinds of questions you'd expect. Now, as far as, so that's what we've got upcoming on the timed lab. All right. Any questions about the timed lab so far, by the way? No?
Next week, right?
This week. 3% of your grade. So not a huge amount, but so this individual one is 3% of your grade. The overall, they're 10%. So not a huge amount, but you want to make sure you do well on as many of them as you can. We'll have one more around the end. We'll have one more basically in the last couple weeks of class. That'll be sometime after winter break. After fall break. Okay. So now, let's talk about, so right now we are going to skip ahead into Chapter 9, and we're going to pull some things forward from Chapter 9. So I don't generally go over Chapter 9 very much, other than to like say these things exist, these concepts exist. So in fact, aside from taking about 10 minutes before the lecture, the morning lecture, I didn't really flip through the slides much. What I care about is in particular operation these guys, all these things have in common. So because this ninth chapter is all about self-balancing binary trees, and there's a bunch of different implementations for them. There's AVL trees, they're red-black trees, 2-3 trees, 2-3-4 trees, and B trees. AVL and red-black are appropriate for this class, and sometimes they're given as homework assignments. I've given them as homework assignments before, just not doing that this semester. What we are going to work on is the rotation operation that the AVL tree and the red-black tree share in common. All right. So the big thing about having a self-balanced binary search tree is that that the performance of binary search tree is proportional to the height of the tree. So let's say you have a perfect tree of height k, then it's going to have 2 to the k minus 1 items. Okay. And if the tree is perfect, or close to perfect, if it's balanced, in other words, what balanced means is essentially that the tree, its left subtree and its right subtree are no more. They don't have a difference in height of more than 1, right? They don't differ in height more than 1, and the subtrees are also balanced. Although red-black does actually expand that to no more than a difference of 2, without actually much consequence at all. The point being, though, is that so long as you start with a balanced tree, if adding a node makes it become imbalanced, then we can rebalance it in log n time at most. So you get log n to add, log n to rebalance in the worst case. That's 2 log n, which is log n, right? So now the reason that this is important is because if you don't have a balanced binary search tree, then this is what, if you don't have a self-balancing binary search tree, which is what we coded up, then we can run into a situation like this. So this is a unrealistic example where basically I would add 1, 2, 3, 4, 5, 6, 7, 8, 9 to the tree in order. Now doing so means that every operation is now O of n time, right? Because it kind of more resembles a linked list than a binary search tree, right? Okay, this is more realistic. This is entering the quick brown fox jumps over the lazy dog, right? All those things in the order the sentence occurs. And notice that while it does zig and zag, none of the zigs or zags, none of the going to the right or to the left does what we need for log n time, which is that it cuts out half our search space. It just kind of just winds its way, and there's a couple of dead ends, but otherwise it's not log n time. So what we need is some operation. So what these self-balancing search trees use is an operation that fixes the way this works, that fixes our binary search tree when these occur. And the answer to that, and the operation is what we call a rotation. It's a bit tricky, but fortunately there's very pretty diagrams. I'll go through what the slide has first, and then we'll see what the Wikipedia page has. So what it does is that it changes the relative heights of your left and right subtrees, but it preserves the binary search tree property. So ignore the middle, which is for a second, but this is what we call right rotation, where we got the start, our tree on the left, and then you right rotate it, and then it will end up on the right. And notice what happens. This has this subtree over here has a height of 1, 2, 3. This is a height of 1, right? And over here we see that now that the left subtree and the right subtree have a height of 2. Okay, so doing a right rotation basically balances your. They help balance the heights of your subtrees. Now, how does that work? Well, for a right rotation, which is what we will focus on. Now, there's a left rotation as well, but it's just simply putting a left wherever you see a right and a right wherever you see a left to do a left rotation instead. So we're just going to focus on the right rotation. To do a right rotation, what we do is that we start at the root of the tree or subtree we want to rotate. And what we do is that we kind of just move it down by making its left child the new root of the tree and adopting the new root's right child as our left child. Okay, that seems like a handful and a bit confusing, and it is. Sorry. It takes a bit for it to click. But here's the algorithm for it, okay? So here's our node, same thing, we're just got it. Here's how this works. The first thing we do is that we remember the value of our left child, okay? Remember the value of our left child, which is this one over here. Now, so we set it as temp. Some other people call it pivot. I'm a big fan of calling it pivot. So we say temp is our left node. Pivot is our left subtree. Then we say root.left is equal to temp.right. So we adopt our pivot's right child as our left child. And we'll see why that's a legal thing we can do in a bit. And then we say temp.right. Well, now that you've got my right child, I'm going to make you my right child. All right? And now we make the pivot the root. So notice that basically now this is the left subtree, and now this is the right subtree over here. And so we reorder it, and it now, if we just simply grab the new root and let it and kind of just dangle it, it will it looks like this. Again, this whole nice left-right thing is just simply because it's nice for us humans to look at, as opposed to this, which is exactly the same thing as just what we had there. But Wikipedia does a much better job of not only just showing you what's going on, but animating it. So let's take a look. So the article is tree rotation on Wikipedia. If you Google tree rotation, which is a fairly, really? Come on. If we Google tree rotation, which is a fairly benign operation, it will come up. So again, here's like, here they make it harder than it used to be because they use Greek. But here they're showing that basically the left rotation and the right rotation are symmetrical. So this is how left rotation and right rotation works. We start with the right rotation, Q is the root, P is the pivot. And what we do is that we move pivot up, Q adopts B, and P becomes the new root. Or if we want to see an animation of how that works, which I think actually makes it a lot more straightforward, we've got to do this right rotation with the root. B adopts A's right child as its left child. Now, why is it able to do that? Well, because this subtree over here, this beta subtree over here, right, every element in it is less than B, and it's greater than A. So we can always put it as B's left subtree because it's less than B. So it preserves this property just nice because it's going to be, because it's this subtree is simultaneously less than A, sorry, greater than A and less than B. That makes sense to everybody? Yes.
What if you have something in the left subtree be already rooted?
I mean, that's what A is. It's the root of A's left subtree. There's nothing. What we're doing is that we're making the root of B's left subtree. Right? There's nothing already there, right? So here it is step by step, drawn out, right? What we do is that we find our root, right, and our pivot. So the first thing we do is we say we want to right rotate around this root, which might be the root of a tree or a subtree, okay, which is important to understand, right? We notate what our pivot is. We notate our left child as the pivot. Then we grab our left child's, then we make our left child's right child our left child. Then we make the pivot's right child the root, and that just reorders itself. And what we do is then, to make sure all the changes go into effect, at least in the paradigm we use, is that we return the pivot. We return this new root of the subtree, right? Pivot is now the new root of the subtree. So we return that to the to whoever called the method, so that they can set the tree appropriately, right? There's pseudocode over here for that, right? Let P be Q's left child, set the left child to be P's right child, and then here, if you have to mess with the parents, then that's what you do in the brackets. It's a fairly straightforward operation. The method actually takes only 4 lines in the body to write. Okay, and that is what your in-class exercise is going to be today. So for 5 points today, I want you to implement the rotate right method. Now, you will find in my GitHub link, which you can find through Canvas, you can find a file already just waiting for you, right? So if you go to Canvas and you go to the GitHub link, you can go to data structures, and then trees, and in there is my binary tree class, which runs perfectly well, and it has a toString method, which is very interesting. It uses a preorder traversal, and it indents, and each level is indented. So the root is all the way to the right, then the root children are on the next indent, and then those children respectively are on the next indent so far, and so and it just kind of recursively processes itself. But use that, add the right rotation method to it, test it out to see that it works, and then turn it in. That's your task for the day. It's 5 points. Everybody who works on it will need to turn in a copy. If you work on it together, you'll just need to turn in what you all worked on. That way I can just check it off. So in that case, just be sure to send it out to every member of your group. All right, any questions on this?
Is this under red line or tree?
It's under binary. It's under trees, not under red blacks.